That's great. The next speaker is Martin Schultz of the Competence Center of Berlin, Wasser. It's a famous institute which does a lot of research on bank filtration, for example. He's also a student of the Berlin University, and he will like to tell us about nanoparticles. And I'm very curious what we can learn from him. Martin.
Thank you for the kind introduction. Yeah, my name is Martin Schultz, and I want to tell you something about the results of my diploma thesis about analysis of nanoparticles in treated domestic wastewater for an improved understanding and prevention of membrane fouling. First, a short overview over my presentation. In the beginning, I will give you a short introduction about our research project. And nanoparticles and colloids in secondary effluents. Then about the material and methods, especially about my particle counter. And then show you results from the lab tests and first results of the online measurements of this particle counter. Okay. Yeah, the study was conducted within the project Amsterdam. It's a big research project where the evaluation of the performance of different options for tertiary treatment are tested at the biggest Berlin wastewater treatment plant with the goal of further phosphorus removal, a disinfection, and these techniques should have a small footprint and low energy and resource requirements. The tested options are different combinations of processes. The first is coagulation, flocculation, and microsieving versus the process of pre-ozonation, coagulation, and low-pressure membrane filtration versus coagulation and the dual media filtration. And in my study, I focused on this process. Okay, but what happens to submicron particles during our process? First, we take the secondary effluent as the influent for our plant, or for our pilot plants, and then we find a broad range of submicron particles which are different in size, nature, density, charge, organic, inorganic, and then we do a pre-ozonation, and due to this pre-ozonation, a decomposition of organic molecules can happen, and which are forming smaller fractions, but also a change of the surface characteristics of inorganic particles which are coated with organic layers, and also a microflocculation can happen, and an agglomeration of the particles. Then we add metal salts for coagulation, and and so the particles are agglomerate, but we also add suspended solids. And on the membrane, as you know, these particles, which when they are bigger than the pores, forming a cake, they can block the pores if they have the same pore size as the membrane pores, and the same size as the membrane pores, and they can cause a pore constriction of the membrane if they are smaller than the pores. Okay, and the objective of my study was to assess the fouling potential of a water by analyzing these the particle fraction below 1 micrometer. And if we know what sizes of particles have a big influence on the membrane fouling, to optimize our pre-treatment conditions to minimize these fractions in our water. And therefore, in a pre-study, we are testing a lot of instruments to measure particles in the range below 1 micrometer. We are testing dynamic light scattering techniques and also fluorescence techniques. But in the end, an instrument was chosen, the nanosite, which are using nanoparticle tracking analysis for sizing the particles below 1 micrometer. But I will later tell you more about it. Then, to determine the effect of our pre-treatments on these particles, and the impact of different particle sizes on the membrane performance. And yeah, since 3 weeks we have implemented the tool online, and maybe someday we can optimize our pre-treatment conditions in our pilot units. Okay, but today I will show you these points. Yeah, now let's come to the particle measurement. At first we need a pre-filtration, of course, to remove particles which are bigger than 1 micrometer, because they will disturb the measurement. And then that's the measuring principle of the device. As you can see here, we have a laser beam which goes through the sample, and the particles are scattering light, which are captured with a microscope camera, and a video is captured. And in the third step, a software is analyzing this video, and as you know, every particle, depending on the size, have a different movement because of Brownian motion. And yeah, the software analyzes the way the particle moves, and by knowing the temperature and the viscosity of the sample, it can calculate the diameter of the particles and, of course, the total concentration of the sample. That's our water quality. See, with the influent, you see we have low suspended solids, relatively low COD. And I take this water at first at lab scale and combine a pre-ozonation with 0 to 15 milligram ozone, combined it with 0 to 12 milligram ferric per liter, and make first tests at lab scale with this Amicon test cell to look what filtration performance the water has. This operated with a constant pressure at 1 bar and a flat sheet membrane in dead end mode. Okay, now the lab test results. Here's a measurement of an untreated sample. You see the particle concentration, the number concentration over the particle size. And it was a test on reproducibility, and you see we can really make reproducible measurements also in this organic matrix. And you also see a typical size distribution, as also can find in other types of waters like surface waters, where you have an exponentially increasing number of size with decreasing size. But you also can see at around 100 nanometer, the sensor is decreasing, and the curve goes down. And so we defined 3 ranges. Above 100 nanometers, we can really quantify the particles in our water. At 100 nanometer, we have something like a limit of quantification. Between 50 and 100 nanometers, we can't really quantify the particles, but we can compare different pre-treated samples. And below 50 nanometers, we can't measure anything. Okay. Here you see the particle concentration of different fractions of different treated samples, just to have an example how our pre-treatments affect the particle distribution. And you see that with a coagulation, the total particle concentration is not affected, but we see a shift from smaller fractions to bigger fractions because of an agglomeration due to ferric. And the same with ozone. You also can see the total particle concentration is only marginal affected, but you also can see a shift from smaller particle fractions to bigger ones. The combination of both pre-treatments shows, as shown in other studies before, synergetic effects, and you can reach a further particle removal. Okay. Here you can see the normalized fouling resistance, whereas 1 is the untreated sample, and here you see the normalized fouling resistance at over the ozone dose at different ferric doses, and you see that we can reach a significant enhancement of the filtrability of the sample due to a combination of ozone, or with increasing ozone dosage, and also with increasing ferric doses. Yeah. And then I try to make a correlation between different particle fractions and the filtration behavior. And here you see the normalized fouling resistance plotted over the particle concentration of different particle fractions. And we found in every experiment that we have a very good correlation between the particles, or the particle amount below 200 nanometers, and our filtration behavior and the normalized, or the total fouling resistance. But what's with the irreversible resistance? That's a resistance which can't be removed by a hydraulic backwash. And there we observed another effect, that you see the normalized irreversible resistance over the ozone dosage. And we see that with an increasing ozone dose, we have bad effects and can recover not that much flux as in the untreated sample. But the dose of ferric seems to compensate this effect. And if you look here at the particle concentration, you can see that it's very difficult to understand, but the conclusion is that we can't make an assessment of the irreversible fouling resistance with our analytical technique, because the limit of detection is bigger than the smallest pores of the UF membranes, and so we can't detect these effects which occurs in these ranges. Okay, and now then I was installing my device online. Here you see a picture of our pilot unit. It's a UF pilot unit with two industrial Inge modules, which are operated with constant flux in dead end mode. And I installed the device. I designed an online sampling unit with a pre-filtration, and I installed this device at 2 points in the influent. And after coagulation, directly in front of the membrane. And nowadays it's operated without ozone, only with coagulation. And here you see the first results. It looks a little bit confusing, but the black graph is the particle concentration of the untreated secondary effluent, and the red graph shows the particle concentration after the coagulation. And you see that the removal due to coagulation depends on the initial concentration of the particles. And we have large daily fluctuations, but we find a correlation between the overall flow of the treatment plant and the particle concentration. If we have rain weather events or a daily peak in the morning, we have higher particle contents in the water. But due to coagulation, these peak flows can be compensated. But what's with the filtration behavior in the pilot units? And these are very fresh results, but it needs further long-time tests. But also in our first online measurements, we find a very good correlation between the particle amount below 200 nanometers and the filtration behavior, which is plotted here at TMP. It means a delta TMP. It means that the difference of a TMP in the beginning and in the end of one filtration cycle between two backwashes. It's also an indicator for the reversible fouling, I think. So. Okay. Now I will give a short conclusion. You see, with our device, our device is able to qualify and quantify submicron particles in our secondary effluent down to 550 nanometers. The nanosite can provide an online indicator for reversible fouling propensity in UF polymeric membranes, but it is not yet useful to characterize the irreversible fouling propensity, because the limit of detection is larger than the pore size. But our first online measurements shows, or we can validate our lab scale results by our first online measurements. And in the future, we will try different coagulant doses and types, and also operation with pre-ozonation, and we will also install the device on the ceramic membrane plant, and maybe someday we will have a particle proportional chemical dosing. Okay, then I'd like to thank you and all our financiers. Yeah, I'm done.